Hello. In this video, we want to take a look at some examples of using the root test to tell if something is convergent, if a series is convergent, divergent. So, first example is the series n squared plus n over 3n squared plus 2n, all to the 4n. So, the root test tells us to look at the nth root of n squared plus 9 over 3n squared plus 2n, all to the 4n. As we are looking at the limit as n goes to infinity of the nth root of the absolute value in here of an, which is also the limit as n goes to infinity of the absolute value of an to the 1 over n. So because we're taking this nth root, the nth root and the n cancel in this limit. So we get this to be the limit as n goes to infinity of n squared plus 9 over 3n squared plus 2n, all to the 4th. And because we no longer have an n in the exponent, we can take the limit of that inside piece and then raise it to the 4th. And that inside piece is a rational, where we know how to take the limit of a rational. We have the same degree. So we look at those coefficients. And so that limit of n squared plus 9 over 3n squared plus 2n is 1/3. And we raise it to the 4th from this exponent of the 4th. And this comes out to be 1 over 81. For the root test, just like the ratio test, we compare it against 1. 1 over 81 is smaller than 1. So the series n equals 1 to infinity of n squared plus 9 over 3n squared plus 2n, all to the 4n, converges absolutely by the root test. So there is our first example. We want to look at that limit, cancel any exponent that we can, and then compare it against 1 to find if it converges or diverges. So second example, we have the series n equals 2 to infinity of -1 to the n minus 1, all over the natural log of n to the n. Setting up the root test, we look at the limit as n goes to infinity of the nth root of the absolute value of -1 to the n minus 1, all over the natural log of n to the n. So first, we can use the absolute value to get rid of the -1 to the n minus 1. And look at instead, since the natural log of n as n goes to infinity is going to be positive, positive over positive, this is going to be the limit as 1 over the natural log of n to the n, all to the nth root. So 1 over n. This 1 over n times n cancel each other. We are looking at the limit as n goes to infinity of 1 over the natural log of n. This, by growth rates, or the fact that natural log of n keeps increasing, as n goes to infinity. This limit is 0, and we compare that limit against 1. 0 is less than 1. So by the ratio test, and the root test, you're looking at the root test here. -1 to the n minus 1 over the natural log of n to the n converges absolutely by the root test. So they're pretty quick examples. Not a lot to check other than taking this limit. So 2 more examples. A little bit more going on in this problem. We have the series of 1 plus 4 over k all to the 2k squared. So setting up our root test, we're going to take the kth root of the absolute value of 1 plus 4 over k to the 2k squared. Remember, this kth root means we're taking 1 plus 4 over k to the 2k squared and raising it to the 1 over k power. And we can pass exponents in and out of absolute values. We actually don't need the absolute value here, as there's nothing to make this negative. So passing this inside the absolute value, 2k squared to the times 1 over k becomes the limit as k goes to infinity of 1 plus 4 over k to the 2k. So we have a k squared times 1 over k. One of the k's cancel, but the other one is left. Now, in this situation, as stated before, first, these absolute values, not really doing much here because we're going to infinity. Nothing is making this negative anymore. We can get rid of those absolute values. And this limit here is also the limit as k goes to infinity of 1 plus 4 over k to the k, all of that squared. And this limit inside that parenthesis, I can move this parenthesis around to the outside. That is one of those special limits that were addressed in the first video of this section. This is the limit as k goes to infinity, 1 plus 4 over k to the k, which is of the form limit as k goes to infinity of 1 plus a over k to the k, and that limit becomes e to the a. Matching that form, what's inside the parentheses underlined in red is e to the 4th. And then we have all of that squared. So this is e to the 8th. And e to the 8th is bigger than 1. So the series that we're looking at, k equals 1 to infinity of 1 plus 4 over k to the 2k squared, diverges because the limit is bigger than 1 by the root test. Again, identifying those pieces of the sentence We have the series converges or diverges by the test with our reasoning. Last example is the series n equals 2 to infinity of the natural log of n over n all to the n. We have everything raised to the n power. That is a good clue of the root test. Be really great here. So set up that root test, limit as n goes to infinity of the nth root of the natural log of n all over n raised to the n. The root and the exponent cancel. So this is, we have absolute values on this. But those absolute values, everything is positive. We have the absolute value of ln of n all over n. This goes to 0 by growth rates. We know that n grows faster than the natural log of n. So this limit comes out to be 0. 0 is less than 1. So our series n equals 2 to infinity of the natural log of n over n all to the n converges absolutely by the root test. So there are our 4 examples. If we see something where everything's raised to an exponent of n or k, or n squared or k squared, that is a very good indication that we may be wanting to use the root test. And that is the end of all of the sequence and series tests, or the series tests specifically, to tell about convergence and divergence as we continue on in the next sections into using series to approximate functions.